We're going to do a few more examples of using Nyquist to find basically how many poles in the right-half plane for the closed loop system based on the loop transfer function. So here's an example. Here's the loop transfer function. Just looking at that, there's a couple things we need to figure out. One is P. P is the number of poles in the right-half plane of this loop transfer function. This is in the left-half plane. This is in the left-half plane. This is a double pole at the origin, so no poles in the right-half plane. So in this case, E equals 0. Then we need to find N, which is the number of loops that go around for, we're looking at every point along the real line, which corresponds to a gain K. How many loops in the clockwise direction around that point? And this guy has a double pole at the origin, so we're going to have infinite loops. Here is what MATLAB drew for us from this transfer function. So it goes off to infinity, goes out here and comes back in here. It has a double pole, so that's little n equals 2. 2 times 180 degrees. Each pole at the origin is 180 degrees of this infinite magnitude loop. So we're going to come out of here, start going, and it's clockwise. It's always clockwise. Come out of here, go all the way around, not just 180, but another 180. This one's a little bit deceptive because it looks like you have to go more than 360. And out at the limit, this is basically straight out and straight back. So it's still, this is what it would look like. So this is a clock, follow this. Out here, around, this is a clockwise loop. So we really only have 2 segments of the real line, to the left of the origin, to the right. To the left, pick a point here, go straight off to infinity. Here's one crossing of a loop, clockwise. Here's another crossing of a loop, also clockwise. So n equals 2 to the left of the origin. Out here to the right of the origin, only one loop, and it's clockwise, so n equals 1. Since p equals 0, z, the number of poles in the right-hand plane of the closed loop system, is it's either 2 or 1, so it's always going to be unstable. This is a typo here. 2 plus 0 is 2. So this is 2. I have to fix that typo. So let's do a few more. And actually this and the next 2 are very similar. Let's see, we have one pole at the origin. All these poles are in the right-hand plane. So P equals 0 here. We'll have one infinite magnitude loop, and it will go around 180 degrees. So let's follow it. This is what MATLAB gives us. Follow it off. It always has to continue in the same direction from MATLAB. Be consistent with the original MATLAB graph. Come off here, start going clockwise. 180, come back in here. So this is what it will look like. Know that in here it's clockwise. So here we have 1, 2, 3 sections of the real line. P equals 0. This crossover by eyeball looks at minus 10. So out here, k is greater than 0, but minus 1 over k, which corresponds to the point on this line, is left of or less than minus 10, which means k is between 0 and 0.1, 1 over 10. Anyway, to the left of that, n equals 0. No crossings, so it's stable there. N plus p equals 0 plus 0, that equals 0, that's stable. Here, pick a line, one one clockwise crossing, another clockwise crossing, n equals 2. 2 plus 0 equals 2. It's unstable with 2 poles in the right half plane. Out here, one pole, or excuse me, well, it will be one pole, but n equals 1, one crossing in clockwise direction. And that's where your k is negative. So anyway, that sums it up. Be careful of your inequality. Here's another one that's completely similar. It has no poles in the right half plane, one pole at the origin. Topologically, it's just the same as the previous example. Come out here, do a half loop, half circle, or n times 180 degrees. The only difference is where it crosses over. And this looks to be what we needed to hint. Which brings me to a point. There is a way to calculate exactly where these crossover points are. And in the interest of time, I didn't cover it in my course. It's a little bit tedious. It takes some complex arithmetic that's just kind of algebraically tedious. You want to know how to do it? Look at my notes in my at my website. So this is the same kind of thing. N equals 0 out here, 2 and 2 between there, and 1 over here. Just do your inequality algebra right. Here, everything to the left of the origin, k is greater than 0. And out here, k is, or minus 1 over k, is less than whatever this is, which minus 2 over 15. That inequality algebra, so that's k between 0 and 7.5, that's where it's stable. 0 plus 0. Here it's 2 plus 0. I have another typo, that should be a 2. And then over here, n equals 1. 1 plus 0 is 1. And that's where k is negative. K is less than 0. Oops. I'll pretty much skip this because it's basically the same as the previous two examples. P, no poles in the right half plane, one pole at the origin, so 180 degree infinite magnitude loop. It just has a different crossover. Using the hint instead of the analytical method, it's at minus 5/3. So everything is kind of the same here. Do I have a typo again? I actually have a 2 there, no typo. But the ranges of k's are slightly different because this is a different crossover. One last example and we're done with Nyquist. Here, the loop transfer function is just this guy times this guy, which is that. And notice this is an unstable system. But we can still use Nyquist here, but we couldn't have used Bode here. We have a double pole because this is squared. So P equals 2 in this case. No poles at the origin, so no infinite magnitude loops. MATLAB gives me this plot. This is counterclockwise, followed around. That's another, right here is another counterclockwise loop. So I have 1, 2, 3, 4 sections of the real line to analyze. To the left of here, n equals 0. Between there and the origin, 1 crossing, 2 crossings, and they're both counterclockwise, so n equals minus 2. Over here to the right of the origin, up to this point, n equals, there's 1 crossing, it's counterclockwise, so n equals minus 1. And out here to the off graph to the right here, n equals 0. P is 2 in every case, so add them up. These are how many poles in the right half plane for the closed loop system, this whole system. And you have to do your inequality algebra. Figure out where this crossing is. I can barely read it. It looks like 0.5. This looks like. So do that inequality algebra to know the ranges of the case. But there's only one place where it's stable. That was here. The N canceled the P. And that ends up Nyquist, which ends all frequency analysis, frequency domain analysis. Our next subject will be state space.